Continuing our discussion on log functions, let's look at graphing the function 3 to the power x along with log base 3 of x on the same graph. And let's see what happens. For 3 to the power x, we can get our ordered pairs by plugging in integers, remembering that any non-zero number to the 0 power is 1, and that negative exponents mean we take a reciprocal. And so 3 to the negative 2 power will be 1 over 3 squared, which will be 1 over 9. I'm going to go ahead and graph these points. So 3, 27 is too big for me to graph, but 2, 9 is okay. 1, 3, 0, 1, 1, 1/3, negative 1, 1/3, negative 2, 1/9 will be really small. We draw a smoothed curve to connect the points. This is our function 3 to the power x. Now, since 3 to the power x and log base 3 of x are inverse functions, we can use the table that we created for f of x, 3 to the power x, to generate our table for log base 3 of x. All we have to do is switch the x's and the y's. The x values in f will become the y values in g, and the y values in g become the x values in f. So we already have 27. Let's go ahead and put in 9, 3, 1, 1/3, 1/9. And then for our function g, the idea is we're practicing understanding what this log means. So g of 1 log base 3 of 1 exponent of 3 that gives me 1 will be 0. The exponent of 3 that gives me 1/3 will be negative 1. And the exponent of 3 that gives me 1/9 will be negative 2. And I can use these ordered pairs to graph our log function. So here we go. 27 and 3 is a little bit too big, but 9 and 2 will work. 3, 1, 1, 0, 1/3 and negative 1, 1/9 and negative 2. And we connect these with a nice smooth curve. And here's our g of x function, log base 3 of x. Some things to point out. If I draw a diagonal line here, right through the origin, notice that these two graphs are reflections of each other across this diagonal line, which is y equals x. They are inverses of each other, and we can see that in the graph. Take a moment to graph the function log base 1/2 of x. Pause the video, try it on your own, and then resume in order to see what your graph should look like. Try to determine if you want to use this table or if there's another way that you could generate the ordered pairs in order to graph. Pause that video, try it on your own. See if you've got a little bit of understanding before plowing through and seeing the answer right away. Now, did you get a graph that looks like mine? I did a little bit of extra work. I started with the inverse function 1/2 to the power x, mostly because it's a little bit easier to think about exponents in this form, 1/2 to the power x equals y, and then taking those numbers and switching the x's and the y's to get the log. So I formed my table for 1/2 to the power x, wrote those y values in the x column, and wrote my x values in the y column. And I was able to get this purple graph for h. Just to demonstrate again the properties of these inverses, I graphed the inverse function as an orange dotted line, which I'll now make solid so we can see it a little bit better. I drew that line y equals x again. So we can see that these graphs still are reflections across that line of each other. Let's identify some comparisons next. Given what we know about exponential functions, let's create a list of what we know about log functions. Starting out, exponential graphs for a to the power x if a is greater than 1. We saw that these were growth functions that were increasing from left to right. The domain is negative infinity to positive infinity, or all real numbers. The range is 0 to infinity, and the asymptote is at y equals 0, or the x-axis. And the point 0, 1 is on the graph. That's our y-intercept for our exponential functions. Similarly, our log functions are also growth functions, as long as a is greater than 1. Since the logs are inverses of exponentials, the domain and the range swap places. So the domain of our log functions are 0 to infinity, and the range of our log functions is negative infinity to infinity, or all real numbers. Also, with respect to the domain, there's an asymptote at x equals 0, the y-axis. And then at the end, we don't have 0, 1 on the graph, we have 1, 0. And it's not a y-intercept because the log functions never cross the y-axis. This is an x-intercept. All of these are true if our base is greater than 1. For bases between 0 and 1, there's a different story. For exponential graphs, we have a decay function. It decreases from left to right, but everything else stays the same. Our domain is still all real numbers. Our range is 0 to infinity with an asymptote at the x-axis, and the point 0, 1 is on the graph as the y-intercept. So when we look at the corresponding log graphs, they are also decay functions. Just like before, we switch the domain and the range. The domain of the log function is 0 to infinity with an asymptote at x equals 0, and the range is all real numbers, and the point 1, 0 is on the graph as the x-intercept. Notice, no matter which type of base we have, the domain, the range, the asymptote, and the intercepts are the same for exponential functions, and they're the same for all log functions. And a disclaimer, we're talking about exponential functions and log functions that have not been translated or reflected, just exponent or log. Now let's consider log functions that have been transformed. So instead of just looking at log of x, now we're looking at some translation, reflection, or scaling of that log function. We have 3 functions on the left and 3 graphs on the right, and we need to determine which function goes with which graph. And we're going to do that by looking at the domains. Since the domain of log functions that have not been translated is 0 to infinity, because we cannot take the log of a number that is 0 or negative, there's no way to give a positive number an exponent and get back an answer that's 0 or negative. And so that's why we have this restriction on the domain for log functions. We want to find the domain of the functions and match them to the graph. In our sample log function, log base a of x, we just have x, and our domain is 0 to infinity. This essentially means that whatever's the argument of that log, we want that argument to always be greater than 0. So we're going to look here for this first one. The input for the log, x plus 5, must be greater than 0. I don't want anything to go inside that log that is 0 or negative. This is very similar to what we did when we talked about radical functions and we took the stuff underneath the radical and set it greater than or equal to 0. We can take even roots of 0. An even root of 0 is just 0. And we can take even roots of positive numbers, which is why we had the input to be greater than or equal to 0. But for logs, we cannot take log of 0, so we make it strictly greater than 0. Solve for x, we can subtract 5 from both sides, and we get x is greater than negative 5. Well, if x is greater than negative 5, that means our domain will be negative 5 to infinity. And we just need to figure out which graph corresponds with that. And we'll do that in a minute. Let's just do the domains first. For the second function, h, log base b of 8x minus 16, we'll take the inside 8x minus 16 and set it greater than 0. Solving for x, 8x is greater than 16. Divide by 8, and we get x is greater than 2, which would correspond to 2 to infinity. See if you can do the last one on your own. Solve for x on that one. 15 minus 3x greater than 0. I'll let you try it, but I will tell you that the domain will be negative infinity to 5. And now, looking at these three graphs all together with our domains, let's try to match them up. I look at the first graph and I see that it looks like there's an asymptote at x equals 2. Well, our original log function has an asymptote at x equals 0, and 0 to infinity is the domain of the original simple log function. This asymptote of x equals 2 means that the first graph corresponds to the second function h. I start at 2 on the domain and I go to infinity. Looking at the second graph, I can find that graph's asymptote, and it looks like that graph's asymptote is at negative 5. And the function that starts at negative 5 and goes to infinity is the first function, g of x, which does indeed lead the last one, the last function, to be m of x. And I look at my domain and compare it to the function, just making sure that it makes sense. The third function has an asymptote of x equals 5, but instead of going off into positive infinity, it's going negative infinity. It starts high and then goes low, and so sure enough we have a match there. In general, given a logarithmic function, to find the corresponding domain, we're going to set the input greater than 0 and solve for the variable. And that'll be how we can find the domain of log functions.